Alrighty. Hello, I'm Rundong or Kevin Tian. Today I'm presenting MyPart, a low-cost, accurate personal air quality monitor. And this was work done at UC Berkeley with my collaborators, Dierk, Chris Myers, and also Eric Paulos. Right, so to begin with some motivation, the World Health Organization estimates that over 3.7 million premature deaths occurred in 2012 as a result of air pollution. The primary pollutant really was particulate matter, airborne particulate matter of 10 microns or less in diameter, which tend to get into your lungs and then cause cardiovascular or respiratory diseases. The issue with these is that they're extremely harmful to human health, but at the same time, it's not always easily perceptible what the air particle pollution is like in your area. Right, so to find out information about air quality sensing, what can you do? So one way is kind of the distributed approach. In the US government, air quality maps are provided by the US government to tell you about the air quality in your region. These maps are typically created using highly expensive calibrated instruments located in fixed locations, and then they're coarsely distributed, and then the maps are then generated by interpolating between those stations. So there's a few issues with that. One issue is the granularity. So air particulates can really differ at a street-to-street level. One issue is that these are outdoor sensors, and they don't really say anything about the indoor quality, which is typically where we spend most of our time. And thirdly, it's not a really personal experience in terms of the data collection or the device interaction. Personal air quality sensors do exist, and I would say that the three most important metrics for these types of sensors are cost, so how accessible are they to a wide audience, their accuracy, how much can you trust the data that's being given, and also its portability, so its ability to function in a variety of environments, not necessarily just kind of hanging on your wall. Okay, so to start off, at the kind of high end of the spectrum are sensors like the MET1. They're highly expensive, highly calibrated, and really intended to be used in these clean room applications to gauge how well your HVAC system is working. They have good portability. It does have an onboard battery, but it is kind of this clumsy device that weighs roughly 2 pounds. They're sensors like the MET1, or they're sensors like the Paulos, which is kind of middle of the pack in terms of cost and accuracy, but the portability is quite poor. If you take the sensor out into sunlight, the sunlight will bleed into the optical sensor and then really mess with the readings a lot. There's also these low-cost sensors that exist that are pretty inexpensive, so $10 to $20, but also rather small. Typically, they're relatively inaccurate and the burden is kind of put on the designer to then integrate this into some other device. So what I'll be talking to you guys today is MyPart, the sensor that we developed ourselves, lacking kind of existing solutions in the current landscape of sensors. The bill of materials is under $50. We've shown that it's pretty accurate, which we've correlated against the sensor on the far left. And then the portability is also quite good. The final size is 50 by 40 by 25 millimeters, and it's roughly the size of kind of a large wristwatch. Yeah, we're really informed by this broad range of prior work, some that focused on on-body personal sensing, and also work that's focused on kind of these DIY toolkits to invite broader participation into air quality sensing. And also this really wide range of projects that looked at how air quality sensing can be incorporated within a wide range of form factors, ranging from wearable T-shirts to carrier pigeons and even to bicycles. But the issue with these projects is that none measure particles. So these other metrics are really important as well, such as carbon monoxide, ozone, sulfur dioxide. But the most important for human health is really the airborne particulate matter. And there's also been kind of this flurry of activity within the startup Kickstarter landscape as well. But some of those same problems exist. Many use gas sensors. Many repackage existing low-cost dust sensors that weren't really accurate to begin with. And also, they're sold as these one-size-fits-all solutions and really restricts the customizability, and I would argue restricts the level of engagement people have with this technology. So the four main metrics that we're trying to hit when building the sensor is portability, accuracy, accessibility in terms of the low-cost components and the fabrication tools required, and also its adaptability. How modular is it to be incorporated into a variety of form factors? So I believe that when we do hit that sweet spot, we kind of we really invite broader participation by creating a sensor that creates usable, meaningful, and appropriate data for different contexts and communities that want to use the sensor. So in the remainder of the talk, I'll talk about optical sensing principles in general, And then I'll talk about our particular design in terms of the mechanics, the electronics, and the software that enabled the smaller form factor but yet maintain the accuracy. I'll talk about the interactions that we designed with the sensor and also end with the user study. So air particle detectors, many of them work like this. The main idea is that you have some sort of focused light source and also a photodiode. You draw air in through the system, which contains particles. As the particles intersect the light source, the light is scattered, and that light is captured by the photodiode, and that signal is amplified and then analyzed to detect how many particles there are in the air. So kind of the two issues with these sensors is, one, the size can be driven by the size of the light source and photodiode, so the distance between those two elements and the optical elements in between. And also, because they're optical sensors, not only does the photodiode respond to the particles scattering the laser light, they also respond to ambient light. So to kind of address these issues, we went through really just many, many generations of these designs that, tried out different arrangements of the air channel, of the laser and sensing, of the fan and battery. We kind of started with these initial laser cut prototypes and then transitioned to these more 3D printed prototypes as we realized how complex the flow geometries needed to be. And this is, of course, kind of the abridged history of the design iterations, and this is the real history for just the bottom row. Yeah. Okay, so diving deeper into the mechanical design, here is an exploded view of the MyPart device. For reference, that inlet port at the left is the same inlet port that you see at the bottom left of the exploded drawing. So here I'll point out some of the most important features. To make it as small as possible, we've located the laser to be at the diagonal of our rectangular device. For ambient light rejection, as you can see, the blue line kind of indicates the path of air as it enters the system. And as you can see, both the inlet and outlet have these bends and turns that prevent ambient light from directly entering the system. And so most of these, oops, sorry, skipped over that. Most of these parts are 3D printed with the exception of the PCB, laser, fan, battery, and I'll talk about the PCB next. So in terms of the electronics design, one of the main points is that we have a high gain photodiode amplifier that's pretty sensitive to noise. So to kind of deal with that, we separated our digital and analog circuitries entirely with separate voltage regulators. So with separate voltage regulators. So conveniently, this actually lets us to turn off the entire analog portion of our circuitry when the device is not in use. So to call out some of the integrated circuits that we used for this device, we used the RF which is a microcontroller that has both the computing but also the Bluetooth radio. We have other chips for charging the battery, for GPI expander, LED drivers, and more information can be found in our paper. Right, so this is a typical signal trace seen by the analog to digital converter after it's gone through several stages of amplification and filtering. To count particles, we use a very basic scheme to just pick a count threshold above the noise floor. More advanced techniques can certainly be used, for example, those that consider the pulse width, those that consider the signal in the frequency spectrum, and also those that consider the signal at various points of its amplification. But we found that with this technique, we can actually get fairly good results. So in this particular test, we wanted to see the performance between our sensor and the MET1 in a variety of locations, both indoors and outdoors. So on the y-axis, we have the counts from the MET1 sensor, and on the x-axis, we have the counts from our sensor. And as you can see, we have fairly good correlation between the two. Okay, talking a little bit about the interaction design. To initiate a reading with our device, the user presses a button on the face of the sensor, and the lights, the scattered light array on the face of the sensor light up to indicate that a reading is being taken. Once the reading is finished, the number of lights and the intensity of those lights kind of indicate in an ambient way the number of particles that the device sees. In addition, we've designed this to work with the mobile app. So once it's finished sensing, it is also broadcasting that information over Bluetooth to the mobile phone. And then I'll talk about some of the interactions with the mobile phone app on the next slide. So again, we have this kind of We have this ambient display, again, to kind of mirror the, this ambient display that shows the particles floating around in this playful manner. We can also swipe down, I believe, to get the particles to stack up into into kind of this bar graph display. And lastly, we have this historical view where we can scan through the times at which we've taken readings. Okay. So for our preliminary user study, the main goals was to gauge the initial reactions with using our device, both in terms of the physical form factor as well as the mobile app. And also, we wanted to ask users about their envisioned usage of this technology. So the setup for the user study was in total 6 participants, 3 male, 3 female, ranging from 18 to 59 years old. And the procedure included an introductory interview, a walkabout, and a follow-up interview. So I'll describe the walkabout next. During the walkabout section, we asked the users to go to 8 locations in an urban environment that ranged from a variety of indoor to outdoor environments. And these environments were really chosen to get them to think about the air quality in relation to that particular place. So these included places such as a bus stop, a library, and also a construction site. So several themes emerged. And the first one that I'll talk about is a general lack of knowledge about air quality. So consistent with previous studies, most users were not very knowledgeable about air quality, how it's measured, or how it's reported. More specifically, there was definitely a mismatch between the perceived and actual air quality. So one user said, well, I usually think I smell something when I think about air quality. It's interesting to see the readings with no way to detect otherwise, and that odor makes no difference. We also asked users to comment on the physical form factor. So within the context of this 30 to 40 minute walkabout, most users thought that it was pretty comfortable and lightweight to wear. However, we engineered the device to be as small as possible, but we did understand going into this user study that it was still quite large to be this wrist-worn form factor. And as expected, we definitely saw some pushback, or not necessarily pushback. We did see that the users responded to that in the user study. However, the idea behind choosing this particular location was to really provoke users to think about kind of these other form factors that could be about on-body sensing or wearables. So when asked about alternate form factors that these users could imagine using, a variety of objects came up, including bicycles, briefcases, phones, and also necklaces. So one thing that points to is kind of this need for customizable design, not necessarily one size fits all, especially when people want to use the sensor in a different variety of contexts. Right. Next, I'll talk about engagement and personal curiosity. Though not required, many users took additional readings while they were on this walk. And in particular, one user said, when asked about where they would use it next, I live in the northwest part of the city, and I'm curious about the factory sound there. The air quality definitely seems different on different days. In addition, many users described other places that they would take this sensor from places that they spend a lot of time at, for example, their offices or their cars. And also, many users showed a desire to kind of share the sensor with other communities, for example, sharing with a group of mothers who had children, or sharing with one particular user said that she would want to share it with her grandfather who lived in India. So in addition to the size, accuracy, and portability, one central element of this design is that it could be kind of adapted to a variety of form factors. So here, in addition to the watch, we've designed these prototypes that are for example, the carabiner, the backpack strap, and also incorporated within a children's toy. And I think that this is especially relevant as digital fabrication becomes more commoditized and personal production becomes more democratized. So according to one statistic, in 2016, the number of active or planned makerspaces has grown to over 1,400 in 2016. And so one theme that we're seeing is that more and more people will have the tools and access to the tools that can make this device completely from scratch. So we really want to tap into this rich ecosystem, and all of our design files will be released open source. And the idea is not only to invite broader participation into the use of these sensors, but also into the design, the customization, and the co-authorship of the sensor for specific people and contexts. All right, thank you very much.
Hi, I'm Manoj from Delhi. I have a question. The sensitivity curve that you showed for the kind of curve that you showed for the correlation between the highly sensitive equipment and the other one with the MyPart, yeah. Was it for PM 2.5 or PM 10? And how that slope varies when you have different diameters of that particular matter?
Right, absolutely. That's a great question. Oops, sorry. Let me find that slide really fast. Yeah, so this, the particles that we're seeing, we're simply basically choosing a threshold above the noise floor. To really get at, to really calibrate that sensitivity well, what you would have to do is get basically a test chamber and then release particles of exactly known distributions.
So this is kind of an open ambient environment kind of test?
Right,
or
so this was kind of, and that was kind of the purpose of this test, to test it in these ambient environments that range both from these indoor and outdoor locations to see if the light leakage was an issue or to see if the different sunlight conditions were an issue.
And have you tried any sensitivity analysis on the sensing part? Have you tried any sensitivity analysis for the sensing elements? Like how good is the temperature variations and the other?
That we haven't examined. That would definitely be future work. Yeah.
Okay. Thank you.
Thank you.
Hi, I was wondering if you're planning to open source the design and what's the battery life?
Could you repeat the question? I'm sorry.
Yeah, sorry. How about making it open source and what is the battery life?
Sorry.
Battery
life?
Oh, the battery life. Great. Yeah, we definitely want to make this device open source. The current battery in this particular form factor is 400 milliamp hours. We haven't done. Yeah, I think the 400 milliamp hour battery roughly lasts a few hundred sampling cycles, and then in between we drop everything, microcontrollers to all the different ICs into a low power sleep mode. But the other point is that it is a totally open source design. The battery compartment was designed specifically to fit underneath at the very bottom of the device, so that you can imagine having that be instead a trapdoor that drops into a bigger battery compartment where you can put in a much larger battery for these data logging applications.
Sorry, so with the one that you showed, like how often do you have to recharge it? Like every day, every 2 days, every week?
I would say probably on the order of every day.
Okay.
Yep.
Are you guys keeping the data and planning to, I guess, correlate or have that available based on location so people can see how or tracking the air quality?
You mean once we have the data onto like the mobile phone, what are the different ways that we can use it?
Yeah, or what happens to the data, I guess.
Currently it's designed to live kind of. It gets offloaded onto the mobile app where it's saved, but we can definitely envision other applications where this, is broadcast to a wider network of sensors where people can see the, sensors from other people and from other places.